Okay, welcome to Year 9 Science Online with Any Van Vieren. Good morning, guys. I hope you guys are all well and that you had a great weekend. Yeah, this afternoon we'll learn some more about where are we going with this lockdown. But in the meantime, we need to continue because we only have 2 weeks to finish this whole thing and get ourselves ready for the test. So, without further ado, I just want to jump us back into our presentation. Firstly, I want to say thank you to the following guys: Hugo, Jake, Mike, Max, Oliver, Richard, Jake, and Sam. If your name is not on here, you really need to ask yourself why not. Because I asked you all to do some homework for me and actually do the electron configuration. Now, guys, in general, I don't ask you to do homework just for the sake of keeping you busy. Okay, this is really important. When you look at our specific learning outcomes, I can take you up here, and you can see here that SLO2 is draw an atom of the first 20 elements showing protons, neutrons, and electrons. Okay, again, only 8 of you did that for me. Then write the electron configuration or arrangement of the first 20 elements, and only 8 people did that. So does that mean only 8 of you is going to get merit or higher? It's something you really need to ask yourself. How much do you think you are doing yourself either a disservice or a service to reaching your full potential? I know it's not easy during lockdown, but seriously, guys, can we try a little bit harder and make sure that you know how to do these things? Okay, but we have to move on because time waits for nobody. Okay, and today we're going to talk about compounds and mixtures. So the specific learning outcome number 4 is define the terms element, compound, and mixture, and be able to give examples. And for merit, you can compare elements, compounds, and mixtures in terms of particle makeup, link the numbers in a chemical formula to the number of each type of atom in that formula. Alrighty, here we go. So, what is an element? An element is a substance made up of only one type of atom. Okay, in this case, you can see here that it's oxygen. But can you see those oxygens are bound together? They form a molecule. Whereas over here, what does Au mean? Au means gold. Okay, and here's silver. What is silver? Is Ag. And what's this one? Copper. But can you see that argon, silver, copper, gold, they are not bound together. They are single elements, whereas oxygen is a molecule. And we'll get to that in the next slide. But everything in here is made up of only one element. This is liquid nitrogen, which is awesome to play with. We're unfortunately not allowed to do that in schools. But liquid nitrogen contains only nitrogen. Copper contains only copper. Pure coal contains only carbon, and pure diamond, guess what, contains only carbon. These two things are made of the same thing, but the arrangement of those carbon molecules are very different. Silver, and for those of you who have an eye for detail, have a look at this. That is actually a picture of Nazi gold. You see the swastika there? And the terrible thing about these ingots, they call them, so 1 kilogram of fine gold, 99% fine means 99.9% pure. But the terrible thing about this was a lot of this gold was actually extracted from people's teeth. The Jews and other people that they put into the concentration camps, before they would send them through the gas chambers, they would literally go through all of their mouths, and if they have any gold fillings or anything like that, they would pull it out so they can purify their gold, which was awful, awful, awful. And we should never, ever, ever have a repeat of that. But anyways, I put that up there just for an interest sake. So an element is a pure substance made of only one type of atom, and it cannot be split into simpler substances. An elemental molecule is a pure element, but they came together to form one molecule, like hydrogen, H2, oxygen, O2, nitrogen, N2, chlorine, Cl2, bromine, Br2. Can you see that they are the same? So they are an elemental molecule, pure element, but they have formed a molecule. If this was gold, we would have a gold molecule and a gold molecule. A gold element and a gold element. They do not, or atom, they have not formed a molecule. The difference between a molecule and an atom is that an atom is a single element, whereas a molecule is two single atoms or more atoms that have reacted with each other. And if they are from the same element, we call that a pure element. Okay, so what is a compound and what is a mixture? A compound is complex. It is complicated. You hear all these words? Okay. Compounds are chemicals made from atoms of different elements joined by chemical bonds. They are complex. What is this? H2O. Do we have more than one type of element in here? Yes, we have hydrogen. How many hydrogens? 2 hydrogens. How many oxygens? Only 1. What does it make together? It makes water. But can we have pure water? Yes, of course. So there is a pure compound, just like pure carbon dioxide, CO2. But is this a pure element? No, because there's more than one element in there. You guys see the difference? Now, how do you get the hydrogen to release the oxygen? Can you separate them easily? No. So compounds are molecules that have been made between different atoms of different elements joined by chemical bonds. They can only be separated by a chemical reaction. It's a molecule with more than one element. Excuse me. A mixture is made from molecules of elements and compounds that are simply mixed without any chemical bonds. If I take a packet of M&Ms and I throw them out on the table, they are a mixture of M&Ms, but in there we have sugar in the form of glucose, we have fats in the form of butterfat, we have the cocoa, we have so many other things, but it is basically, when you think about it, that's a mixture. Over here we have a mixture of seeds, and he's slowly but surely separating them. Over here we have a mixture of vegetables. They did not react with each other, but they came together and they formed a beautiful soup. Okay, so mixtures are things we can easily separate. But a compound has chemically reacted. Mixture, no chemical bonds. Compound has chemically reacted. I hope you all understand that. So compounds made up of 2 or more elements formed by a chemical reaction and joined together by chemical bonds. After the bond is formed, the compound may have completely different properties compared to the elements it was made of. For example, sodium. Do you remember that video I showed you of the guys who threw the brick of sodium into the pond and it exploded big time? So here we have a metal that when it reacts with water or oxygen, it actually explodes. So it wants to kill you. And chlorine. Why do you think we put chlorine into swimming pools? It's to kill all the germs. Chlorine gas was used in the First and Second World War for warfare, to kill people. Chlorine is highly toxic. So holy moly, we take an explosive metal that wants to blow you up and a toxic gas that wants to kill you. We have them react with each other, and what do we get? We get sodium chloride, table salt. And you put that on your food all the time. How weird is that? When you think about it. Explosive, toxic, yummy. And it just shows you, when those chemical bonds form, they have completely different properties. Now compounds, remember compounds, more than one element that has molecularly bonded. Because compounds are formed from chemical reactions, they also need to undergo chemical changes to be separated back into their individual compounds. So for example, water can be separated into hydrogen and oxygen molecules using an electrical current. This is called electrolysis or hydrolysis. So we can take that, but to separate the hydrogen and the oxygen, we need to put in a lot of electricity. Now, a friend of mine, he was actually an engineer on a nuclear-powered submarine. And he had to take salt water from the ocean, and the first thing he had to do was distill it into just pure water. And then, using all the electricity he got from his nuclear submarine, because they would go underwater for 4 months and not surface. So how do they get oxygen? He had to do electrolysis of water. So the hydrogen gas that wants to explode, he had to pump into the ocean, just in hydrogen bubbles, and that would be fine. And then the oxygen would be used to make sure that the sailors can still breathe. So here's a video of some of the hydrolysis of or electrolysis of water.
In that small plastic container are two metal push pins, and they're inserted a distance that's between the positive and negative lead of the 9-volt battery. So you just insert them in there and make sure that they're that distance apart, and that should be fine. In the container is going to be some water that has baking soda mixed into it. The baking soda in the water allows electricity to flow between the two metal tips of the push pins. And so now you set them on the leads, and the electricity can flow between the two push pins now. And so electricity is flowing through the water, and so that's enough energy to break apart the water, make it undergo a chemical reaction, so that the H2O gets broken apart into H2 and O2. It's going to be hydrogen gas and oxygen gas. And both gases are going to flow up through the test tubes. And one of the gases is going to be in one test tube, and the other one's going to be in the other one. How do you know which one's which? Well, if you take a look at the amount of gas in each test tube, there's going to be twice as much hydrogen gas as oxygen gas. So you can see in the right test tube, you have twice as much hydrogen gas as oxygen gas. This is how experimenters first learn that the ratio of hydrogen atoms to oxygen atoms in water is 2 to 1. It's 2 to 1 ratio, thus H2O.
Okay, so you guys saw there that it takes a lot of energy, a lot of electricity to separate them. Now, if you have a nuclear power plant and you in a little submarine, you have more than enough electricity than you would ever need. But if you are, for instance, wanting to build a hydrogen fueled cell car that only runs on hydrogen, and the nice thing about that is hydrogen, when it burns, it creates H2O, which is water. But to separate the hydrogen and the oxygen takes a lot of electricity. So you're basically putting electricity in, which comes from potentially dirty sources like burning coal or fossil fuels. But if you can get that from clean fuels like wind and so forth, then it's good. And that's how you can actually separate that and make sure that when it burns, it only releases water. Okay, dihydrogen oxide. Anyways, so when you look at seawater, seawater is a mixture of salt and water. But water is a compound between two elements. Okay, so mixtures and solutions, colloids and suspensions. Holy moly. Each component in a mixture keeps the original properties. So in a mixture, they do not react with each other. Okay? The salt is still salty in salt water. The water is still watery in salt water. They do not react with each other. Because mixtures aren't formed, they do not form new chemical reactions, and they cannot be separated by a physical reaction. And we'll get into the difference between a chemical reaction and a physical reaction very soon. So here we go, chemical and physical reactions. So when something has a physical change, it can change size or shape or state. So water in a solid is called what? Yes, it's called ice. Solid water is ice. But liquid water is called what? It's called water. Is it chemically different from ice? No, it's not. So what about water vapor or steam? It's gas. Is it still water? Is it still the same chemical as ice? Absolutely, yes it is. So all of that is called physical changes. If you take your Coke can that's made out of aluminium and you crunch it up, you're changing the size, aren't you? And you're changing the shape. Okay, so you can compress things and you can shape them, but they don't actually undergo a chemical change. It does not form a new substance. Physical changes can sometimes actually be reversed. We can take a gas, we can condense it, turn it back into a liquid, and turn that back into ice. So, physical things, it's not necessarily a permanent change. So, glass breaking, look at that. And bang. That is a physical change. If you go to a lot of the stores these days, like Bunnings, they have fresh peanuts there, and then they can crunch them or grind them into peanut butter for you right in front of you. So you're literally taking peanuts and just grinding them down, and it turns into peanut butter. Is there any chemical change? No, it's still the same chemicals. We didn't have a chemical reaction taking place. If somebody cut your hair, is there a chemical change? No, it's just do not get a haircut like that. Okay, especially you, Ollie. Sorry, I'm picking on you. So here we go. Here's some physical and chemical changes. This is chemical changes. Alright? And, ooh, I will probably be pinged for that song in, so it's a shame because I'll put that video up, a link for you. But there's some beautiful chemical reactions taking place there. So a chemical change allows the following, occurs following a chemical reaction. So common signs of a chemical change or a chemical reaction is a change in color, the releasing of gas, or the giving off of heat. So if you take a match and you set paper on fire, the carbon in the paper is reacting with the oxygen in the air, and that is releasing oxygen gas. Or if you take, like you've all done, you take vinegar, which is ethanoic acid, and you combine that with bicarbonate of soda, which is baking soda, okay, and the two chemicals come together, and what you get is a release of carbon dioxide and water. So suddenly now, carbon dioxide comes off. Can you see that it's releasing a gas? Over here we have potassium iodide. and lead nitrate, and when you put the two together you have this beautiful, beautiful reaction forming. And I wish I could show it to you in real life, but hey, you're going to have to live with the pictures. And again, that other video I will put up so that you can watch my favorite chemical reactions, and specifically the Pharaoh's serpent. You need to watch that, it is amazing. But yeah, when you see a change in color, or giving off of heat, or releasing of a gas, that is all due to chemical changes. So, when you burn wood, that's a chemical change. When you bake cookies, the reactions in there actually changes. And why does bread, for instance, rise, or cookies rise? It's because of CO2 being released. Okay, so that's all chemical reactions. A car rusting, iron rusting is actually a chemical reaction. Alright, so chemical reactions is when the atoms, for instance, they would change partners. So in this case we have oxygen and we have hydrogen and oxygen, and they come together and then they form two molecules of water. So the original substances are called reactants. Reactant is something that's going to react. So the oxygen and oxygen in this case are called the reactants. And when they react together they produce products. Okay, so we have products over there. So reactants and products. Please remember that in chemical equations. Reactants and products. So when you're actually writing a little word equation over here, we have carbon plus oxygen produces carbon dioxide and heat. So carbon that you get in your wood plus the oxygen that you get in the air. Anybody ever told you that a fire has to breathe? So carbon and oxygen will give you carbon dioxide, the gas coming off, and the heat of the fire. So that's the word equation, but we also get a chemical equation. So carbon is C plus oxygen, which is going to be O2. Can you see that is an elemental molecule? Remember, there's more than one. This is a pure element. And put them together and they will produce CO2, carbon dioxide, and heat. Okay, so that's your formula. Over here is your word equation. Alright, so great guys, thank you so much. That's the end of today's lesson. Can you please also check the OLE? I've put some pages for you there to do in your SciPad, just so that you know and understand. And more than that, I will speak to you again in 2 days. Alright, have a great day. Thank you. Bye.